Okay, so here is, we're going to go through an example. We're going to make this really quick today since you guys had, some of you had to finish your test from yesterday, and you should have in your warm-up, should have copied down the notes that I needed you to copy down was the definition of a random variable, and then the whole box that had the discrete random variable, the whole box that has continuous random variable, and then what a probability distribution is, and then what a density curve is. So those were the 5 things I needed on your notes. And what I'm going to give you now on that same page, you can make some notes here, but I'm going to give you an example of a problem that has a discrete random variable, and those are the problems like 1 through 5 that we'll have today. And then I'm going to give you an example of a problem that gives you a continuous random variable. Okay, so this right here is APGAR scores, and it's kind of nice since we've got babies here, but this is a baby's health at birth. So in 1952, Dr. Virginia APGAR suggested 5 criteria for measuring a baby's health at birth: the skin color, the heart rate, the muscle tone, breathing, and the response when stimulated. She developed a 0, 1, 2 scale to rate a newborn on each of the 5 criteria. So the lowest you could score is a 0 on all 5, which would add up to a 0. The highest you could score is a 2 on each one, which would add up to a 10. A baby's APGAR score is the sum of the ratings. Okay, they're still used today to evaluate the health of newborns. What APGAR scores are typical? Well, to find out, researchers recorded the APGAR scores of over 2 million newborn babies in a single year. Imagine selecting one of these newborns at random to find the random variable x. So x is the APGAR score, and the table below gives the probability distribution. So here we have the table, and in the table we have all the probabilities. So if you notice, it's a probability of 0.001 of getting a value of 0, or a terrible score, and also it's a probability of 0.053 is what this last one is, of getting a 10. Again, there's a lot more scores. If you notice, the highest scores are 8, 9, and 10, because overall that's an average baby or a healthy baby. And the lower scores, it's a little bit of a lower probability, because a lot of our babies are healthy, even though some aren't. Most of them are. Okay, so A, show that the probability distribution is legitimate. Now, when they ask you to show that probability distribution is legitimate, what you would be doing is showing. So just on your paper, you would actually write all of these probabilities and show that they all add up to 1. So you would just add them up and make sure that it equals 1. So for a probability distribution to be legitimate, all probabilities here, all of these down here, have to be between 0 and 1, and they are, and they all must add up to 1 when we add them all together. B says make a histogram of the probability distribution, and I'm going to show you that. So this is the histogram, and in a problem, I think problem number, let me look, problem number 4 today, you'll be making 2 histograms. This is an easy histogram. It goes up by 0.1 each time, and that's a good idea for the problem you're doing today, to go up by 0.1 each time. And then it has your 10 scores. And we can see in this that the most common score here is the 8 and the 9. So the healthy babies, which is like 7 and above, is the more common. It's what we most often see. Babies that aren't healthy, we do see some of them, but they are far less common. Okay, we'll go back to part C. Doctors decided that APGAR scores of 7 or higher indicate a healthy baby. What's the probability that a randomly selected baby is healthy? So 7 or higher indicates a healthy baby. So we would go up here and we look at our 7 or higher, and we have 0.099, we have 0.319, we have 0.437, and we have 0.053. Those are the probabilities that are 7 or higher. Type those in on the calculator, and we get 0.908. So there is a 0.908 or over 90% probability that we will end up with a healthy baby, which means that they have a score of 7 or higher. Now, you will notice in a discrete random variable, which is what we're talking about here, discrete means it can't be somewhere in between. So like a baby had to get a score of 0, 1, or 2. They couldn't get a score of half or 0.5. There's no decimals here. So the issue is 7 or higher means 7 is included. Higher than 7 would mean just 8, 9, and 10, but because the question says scores of 7 or higher, that means greater than or equal to 7. So we're talking about 7, 8, 9, and 10. So make sure you realize that in a discrete random variable. So that's your example for discrete. And now we're going to turn to a continuous random variable. So again, we've talked about heights before, but this is young women's heights, and it is a continuous random variable. Problems 6 through 10 today, those are about continuous random variables. Now continuous variables will look like, so we're going back to the normal curve. So if you did problems with z-scores with the normal curve, the mean, standard deviation, all those are continuous. So this says the heights of young women closely follow a normal distribution. The mean is 64 inches. Standard deviation, it says here, is 2.7 inches. So that's very important. So the problem just says, what's the probability that a randomly chosen young woman has a height between 68 and 70 inches? Okay? So what I'm going to do here is show you the mean is 64. Standard deviation is 2.7. We want to know the probability that they're between 68 and 70 inches. So I'm going to put this up here on the screen for you. Okay, so this sets up our problem. This is what we want to know. Now, how we're going to get that is the important part. So what we're going to do to get that is we're going to do a couple things. We are going to go to our calculator. I'm going to show you the easiest way. So we're going to go to second distribution. So you need to be writing the commands here. Second distribution, which is second vars. And we're going to scroll down to normal CDF. And we're going to have to put in 4 things. The 4 things we're going to have to put in are actually given to us right here on our paper. So the first thing we're going to put in, normal CDF will be up on our screen. And the first number we're going to put in is what's called the lowest we want. So we want the probability that they're between 68 and 70. So the lowest number we want is the people who had a height of 68 inches. The highest number we want is those who had a height of 70 inches. So that's the next number we want to put there. Then we've got to tell the calculator what the mean is, that's 64, and what the standard deviation is. That's 2.7. So those are the 4 things that have to be entered. The lowest number we want, which is 68, the highest, which is 70, the mean, which is 64, and the standard deviation, which is 2.7. So your calculator should look something like this here. Okay, hit enter, and you see 0.056. That's at least 3 decimal places is what we need to go. So that tells us there is a 5.6% chance of selecting a woman between 68 and 70 inches tall. Okay, so again, what did the problem say? The problem gave us the mean and the standard deviation, and it asked what the probability was of selecting a woman between 68 and 70 inches tall. So 68 was our the lowest number we wanted, 70 was the highest number we wanted, the mean was 64, and the standard deviation was 2.7. And so we got a 0.056 or 5.6% chance of selecting a woman between 68 and 70 inches tall. And that is an example of a continuous random variable and solving a problem with a continuous random variable.